Ladies and gentlemen, today's video has started. No giveaway today. Sorry. Sorry, it's disappointing. But all right. Today we are going to introduce the idea of the quantum mechanical model of the atom. Before we do that, though, I want to review a couple of things based on the scores that you guys did on the quiz, or that you guys scored on the quiz. We don't need to review this a whole lot, but just kind of remember where we are and what we've what we've done. Let's do some things. So here is a simulation that allows us to build an atom. Okay. So down at the bottom, we have three buckets: protons, neutrons, electrons. And over on the right-hand side, we have three charts that are going to keep track of some things for us. So I'm going to start off, and I'm going to add a proton to my atom. And I'll take it up here and I'll throw it. Oh, apparently I didn't go far enough. All right, put it here, and we go there. Okay? So, a couple things change, right? Let's take a look at three things that change over on the right-hand side. What changed over on the right-hand side? All three things. So let's talk about why they changed. So what? Mass number is 1, because the mass number tells us what, Will? Both on the protons and neutrons. Okay, so we got protons and neutrons. Right now there's one proton, no neutrons, mass number 1. What else changed over on the right-hand side? Go. Plus 1 net charge, right? Because we have a positive proton, but no what? No electrons to balance that out, right? And then the third thing that changed, right? What kind of atom have we created? A hydrogen atom, because we have what? 1 proton. And hydrogen, and 1 is what part, or what factor, and it's the wrong word. What's the atomic number of hydrogen? 1. All right, good there? So let's talk about that, okay? So, Alexa, if we look at our model on the left-hand side, right, it says that it's hydrogen, but it also tells us what? A little thing popped up on the right-hand side over there. Plus ion, okay? So, we talked about the idea that atoms are electronically neutral, and that means what has to be true? To make an atom electronically neutral, it has to have what? How about not just a proton and a electron? It has to have the same number of protons and electrons, right? So in this case, if we throw an electron in there, right? Now it becomes neutral atom. Okay? Good with that? Here, we talked earlier about something called an isotope. Okay? Do we remember what an isotope is, or what our definition of an isotope is? Anybody? Nope. What about neutrons? Not always. Isotope. Not necessarily. Okay. Henry, did you find it on your? Yeah, you have to look back. There it is, Henry.
Atoms have the same number of protons but different number of neutrons.
Okay. An isotope, or isotopes, are atoms that have the same number of protons but a different number of neutrons. So, if I take this atom that I have built up here, and I put a neutron in it, okay, one thing changed. The mass number changed, because mass number is protons plus neutrons. So my mass number went from 1 to 2. Anything happen with the charge? No. Okay? Here, I take another neutron and I put it in the nucleus, right? One thing changed. What changed? Mass number changed, went up to 3. Does anything happen with the net charge? Does anything happen with what type of atom it is? No. So those 3 atoms that I just built, this one, and this one are all isotopes, because they have the same number of protons but a different number of neutrons. Nothing changed about what kind of atom it is, but just what's in the nucleus of that atom. Okay? But when I go here and take this away, now my neutral atom becomes a plus ion. Okay? If I do this, Now what changed? It's a negative ion, right? So, based on that little demonstration, what can you tell me about ions? What has to be true in order for something to be an ion? It has to have a different number of protons and electrons, right? If it has more electrons than protons, what kind of an ion is it? It's a negative ion, right? Net charge, -1, right? There's 2 negatives, but only 1 positive in that section. If it has more protons than electrons, it's a positive ion. Ions are really important when we start talking about bonding, when atoms join together to form compounds. So we'll talk about those in a couple of units, right? For now, we're going to stick with neutral atoms. All right? So, here, okay? I've made myself a neutral atom, right? 2 protons, 2 electrons. Most helium atoms look like this, okay? What would we call this helium atom? Okay. What would be the name of this atom? This atom, it's helium-4, all right? Because helium tells us the number of protons that are in it, and then 4 tells us the mass number, okay? Good with this so far? Okay, so here, one other thing that leads us into the next part, okay? When I start building these atoms, and so we'll build the next one. So I add another proton, another neutron, and another electron. Oh, and another electron, right? And then Jack, this is what? This is lithium-6, okay? But, relating into what we're going to talk about today, when I put those protons, neutrons, and electrons in the atom, they go in specific places, right? Where do the protons always go? In the middle. We call that what part of the atom? In the nucleus, right? Where do the neutrons always go? Neutrons go in the nucleus, right? What experiment discovered the nucleus of the atom? Gold foil experiment, done by? So, we know from the gold foil experiment that protons are in the nucleus of the atom. We learn a little bit later on that neutrons are also in the nucleus. So that then leads us to, okay, well, if we know that protons and neutrons are in the nucleus, electrons are outside of the nucleus, but where outside of the nucleus? So what we're going to talk about over the next week or so with the quantum mechanical model of the atom is, where are these electrons? Can we make a complete picture of what an atom looks like? Protons, neutrons, and electrons. Okay? So before we get into that, we have to talk about another experiment, right, that tells us a little bit about light. Okay? So this simulation is something called the photoelectric effect. Because you know English, you probably could tell me 2 things about the photoelectric effect. It probably has to do with what? Light and electricity, right? Photo is the light part, electric is the electric part, okay? So, a little bit later on, 2 units from now, we will do a unit on electricity. And we will talk about things like voltage and current and resistance. But for now, let's go to a brief introduction. Voltage is basically power. Current is movement, okay? Here, in this little setup, we have a battery. Batteries give power to electrical devices. This battery is charged up to 8 volts, which in the grand scheme of things is not real big, but kind of powerful. But right now, the current is 0. There is no movement. Okay? Why? Because there's a big gap in our circuit, right? current doesn't move if there's a break in the circuit. Okay? That's why, like, most of us probably don't have these anymore, but an old style light bulb, an incandescent bulb that had a little glowing filament in the middle, are we okay with that, right? If that breaks, the light bulb goes out because there's a break in the circuit and nothing happens. Or in something like a light switch, right? When you flip the light switch off, inside of the wall, the circuit comes apart and that stops the lights. Okay? There's a big break in this circuit, so there's no current, there's no movement through this circuit. Okay? But around the time of Rutherford, we found out something that was really did not make sense at the time. But then when we start looking at other things, we start realizing, oh, this is what's going on. Okay? So, here's my circuit, and the battery is like full go, full power, and still nothing happens. Okay? So I'm going to take this battery, and I'm going to move it back down to 0 volts. Alright, so it's not doing anything. But I have a light up here. Okay? This is a lamp. And in it is a light bulb. But right now, this light bulb has a light bulb in it that will give off ultraviolet light. Okay? You guys probably know ultraviolet light, that's black lights. Okay? Black lights you technically cannot see, although all black light bulbs have a little bit of purple mixed into it. That's why things look purple underneath them. But ultraviolet light by itself, you can't see. Okay? So I have an ultraviolet light here. And right now, even though it's kind of jumbled up, the intensity of this ultraviolet light is 0%. The light is not on. But if I turn the light on, even just a little bit, just by shining light on this piece of metal, things start to move. The light makes things start to move, even though the battery is totally at 0. And we get electricity flowing through this circuit just by shining light on it. If I turn the light off, the electricity stops. Eventually, as soon as that one gets across there. If I turn the light on brighter and increase the intensity, what do you think is going to happen? More electricity. So we get a bigger current just by shining light on this. That's good. That has to do with, so those little purple dots are actually electrons. Okay? And we'll find out here a little bit later on that where the electron starts in an atom determines how much energy it has. So that, depending on where those electrons come from within the atom, determines how much energy they have coming out of it. Okay, so that's why. All right, but here's the thing, okay? A little bit later on, I can take this ultraviolet light bulb out of my lamp and replace it with a purple one. So, ultraviolet bulb comes out, purple light bulb goes in. Still shining light, but now what's happened to the amount of electricity? The current went down, right? From about half, okay? Still very, very bright, but not as much current. Okay? Purple light bulb goes out, blue light bulb goes in. Okay? What happened to the current? Went down. Okay? Still just as bright. I haven't changed how bright the bulb is, just the color. Blue light bulb goes out, green light bulb goes in. Oh, let's go a little bit higher on the It's a nice color green, isn't it? Even though the current says 0 down there at the bottom, we still have a small number of electrons that are coming out, but definitely less than with the blue. Okay? Green light bulb goes out, yellow light bulb goes in. And now current totally stops. Okay? It's still very, very, very bright, but still nothing happens, just because of the color. Okay? So, why? That was the question. What's going on here? So what we realize from this is that light actually carries energy. And the color of the light determines how much energy it carries. Remember energy, our definition of energy, the ability to do stuff, right? Yellow light doesn't carry enough energy to make anything happen. We could shine the brightest yellow light on it that we can find. Nothing will happen because that yellow light doesn't have enough energy. Okay? But we put purple in, and we get a whole bunch of current, or way more current than before. Even if we turn the intensity down, so we're not shining a very bright purple light, but still purple light itself has enough energy to make this happen. Okay? Does that make sense? So, the color of light determines its energy. So what determines the color of light? That's what we were trying to get at. Okay? For the record, before we move on to the next part, this part here, if we make this ultraviolet, so now you can't see it anymore. Notice the light is like black, right? It's out of our visible range, okay? But the ultraviolet light is still making this current go. Anybody know where we use this? You probably have one in your house that's set up like exactly like this. No. This is the little seeing eye protector on your garage door opener. Your garage door. Does everybody know what I'm talking? Does everybody know what I'm talking about? Right? Does everybody know what I'm talking about?
Yeah.
Right? The little thing that on either side of the garage door, and if something walks in between it, the garage door goes back up. So there is a beam of invisible light that shines between these two. And the light from one causes the current, and your garage door measures that there is current there. Okay? And when the current is there, everything's cool. But if we turn off the light, or if we block the light with like a dog or a person or a small child, right? Okay, or a cat, okay? What would happen? What happens to the current if we block the light? It stops. And if the current stops, your garage door opener knows that something's in the way. And then it says, oops, better put this thing back up, right? So that's how the little seeing eye thing on your garage door opener works, by something called the photoelectric effect. Okay? That's also why sometimes it can get fooled if you have like a really bright day or something like that. Like if there's like lots of light reflecting, sometimes it can fool your garage door opener because that light is coming from other places besides the other side of the garage door. Okay? All right, so what does this tell us? Well, learning the nature of light teaches us about the nature of matter. And that gets us into the quantum mechanical model of the atom. And we start off the quantum mechanical model of the atom with something called the Bohr model. Okay? So, 1905, Rutherford tells us about the nucleus, doing the gold foil experiment. In the early 19-teens, 1915-ish, something like that, a Danish scientist, who's from Denmark, named Niels Bohr, puts together a model, a picture of his atom. And most of you, if I asked most of you to draw an atom, you would probably draw me a Bohr atom. And a Bohr atom looks like this. Boom, here it is. Okay? When we were building this atom, things go in certain places. Protons go in the nucleus, neutrons go in the nucleus, electrons go on these rings outside of the nucleus. Okay? So what Bohr figures out about the structure of the atom is that electrons exist around the nucleus in these very defined shells, or sometimes we call them orbits. And not only where the atoms or where the electrons existed, but why they existed there. That these shells are related to the amount of energy that the electrons have. Electrons that are very close to the nucleus have a small amount of energy. Electrons that are farther away from the nucleus have a bigger amount of energy. Are you doing some more stuff? Okay. So, gotcha. No. Shells close to the nucleus contains lower energy electrons. For some reason, that's number 7 on your outline instead of number like, I don't know. So, all right, good with this? Going back to this picture, okay? When I take, that worked better than I expected, all right, so when I put this electron in, right, it goes onto that ring. When I take one of these rings out, or when I take one of these electrons out, that one from the next shell falls down to the lower shell. Why? Because that first shell is the lowest amount of energy that an electron can have. And that's good. Baseball. If I hold the baseball up in the air, what would we say about its energy, or what kind of energy it has? It has a lot of potential energy, right? But if I let it go, where will it go? Down. Why does it go down? Gravity is how it goes down. Why does it go down? What happens to the potential energy as it goes down? It decreases. What we find out there in the universe is things will try to get to a lower energy state. The lowest energy state possible. This baseball, if I pick it up in the air, the first chance it gets, it goes back down. Why? Because this is the lowest energy state of the baseball. Where do electrons automatically go if they can? The lowest energy state. But just because that first ring is the lowest energy state for electrons, or the floor is the lowest energy state for the baseball, doesn't mean that we can always get there. Let's say that I had enough baseballs to cover the entire floor with baseballs. Alright? If I dropped one more, would it make it to the floor? No. But it would go as low as it can to get as little energy as it can. Same thing is true here. Electrons try to go to this first level because this is the lowest energy they can have. But if that level is full, they'll go to the next lowest one they can find. If a space becomes available in that lowest energy level, they'll move there. Just like if I took one of the baseballs off the floor, this baseball would try to find its way back there. Right? Good, good. No. That's what we'll talk about next week. We'll talk about where are these energy levels and what do they correspond to. But right now, all you need to know for Bohr's model, closer to the nucleus, lower energy. But they don't make it all the way to the nucleus. Okay? Well, go ahead. Say again?
This is relevant to the chart.
Okay.
When it shows the mass numbers, is that just because the electrons are in it? Why is all the protons?
Okay. what did we say about the mass of an electron versus the mass of a proton and neutron? It's really, really small. It has some mass, but it's very, very small compared to, it's just irrelevant as far as like the total mass of the atom is concerned, okay? All right. So the one analogy that we always use to describe the Bohr model is a ladder. These shells that Bohr described for the electrons are kind of like the rungs on a ladder or the steps on a ladder. You can only exist on a ladder on this step or the next step or the next step, right? You can't be in between steps on a ladder. Same thing is true of Bohr's electrons, right? When we go here, these electrons are either on this ring or on this ring. Even if I try and drop it off in the middle, it doesn't stay there. It goes to one of those rings. Okay? That's what Bohr was saying about the electrons in this model. They have to be either on a shell or on the next shell, but they can't be in between. Now, like we saw in the model that we've been using, the reason why is that Bohr is he describes these levels as being quantized. They contain certain amounts of energy. The photoelectric effect goes a long way to describing energy in this way. You can't have any amount of energy. There has to be a certain amount of energy. And every other amount of energy is a multiple of that lowest amount of energy. If I say those words, do they make sense to you? Right? So, another example of quantization is money. What's the lowest amount of money you can have? No. A penny, right? That's the lowest amount of money you can have. Well, I suppose 0 is close enough, right? If you have money, it comes in a penny. Every other amount of money is some multiple of a penny, right? $1 is the same as how many pennies? 100 pennies, right? Okay? You can have $100,000 worth of pennies. It's still an integer multiple of a penny. Does that make sense? Right? So, same thing is true here on the ladder. You're either on this step or on this step or on this step, but you can't be in between. Okay? Yeah, these shells are quantized. Okay? Now, as we saw in the model, electrons are not stuck on their ring of the ladder. Okay? You can move between one shell and another shell. But the only way you can do that is by gaining energy or losing energy. If you gain energy, which way do you go? You go up the ladder. Just like when you go up the ladder, what happens to your potential energy? It increases, right? You can move down the ladder. That means you have to lose energy. Okay? What we find out is that light from the photoelectric effect and what it does, that light allows those electrons to move up the ladder and in some cases completely off the ladder if there's enough energy. Okay? And so, you know, or these electrons know, exactly how much energy you have to gain or lose, because we know where those levels are. Just like on a ladder or on a set of steps. You know how much energy you have to gain. You have to step this high to get on to the next step. If you don't step that high, where do you end up? Well, or if you're already up the ladder, right, you end up on the step that you started on, right? Is it possible to move 2 steps at a time? Yeah, right? You can move 2 steps at a time if you take a bigger step. Same thing is true of these electrons. They can jump 2 or 3 or 4 levels at a time if they gain enough energy to do it. Same thing is true about coming back down. They can fall from step 7 to step 4 if that's the amount of energy that they lose in doing so. Okay? All right. Understanding Bohr's model, are we okay with that? Okay. So, here's the problem. Bohr's model has some limitations, and here's the limitation. Bohr's model works great for hydrogen. It explains hydrogen really, really, really well. Knowing what you know, what do you know about hydrogen?
It's simple.
It's very simple. It only has how many electrons? 1. And how many protons? 1. When we start throwing in more protons and more electrons, Bohr's model, it just doesn't quite do it. It's close to explaining what's going on, but it doesn't quite cut it. And the one thing that gets thrown out of the window is this idea of the rungs on the ladder. So, Monday, we will get into how do we go from Bohr's model, the rungs on the ladder, to what we refer to as a Schrodinger model, which talks about electron clouds. So we'll talk about that on Monday.